Okay, we're going to talk about two different types of gravitational potential energy that we can calculate in physics. One is going to be when we're close to the surface of the Earth, and another one when we're further away. So when we're close to the surface of the Earth, we've got a simpler calculation, and I've already seen something like this. If I can find my, there it is. So for potential energy in this class, we're going to use U to represent potential energy, and we'll give it a small g to say gravitational. When I'm close to the surface of the Earth, we'll use mg and h, right? So here I have some 0 point. I decide this is 0. If I have something that's some distance above that, h, say I have a box, there's some distance above that, then I can determine the gravitational potential energy. This 0 point is arbitrary, right? So you get to decide this, right? So if you decide, well, I want to set my 0 point down here, you can do that. Right, as long as we're close to the surface of the Earth, that it should work out fine. So really, we're looking at is the difference in height between your 0 point and wherever that thing is. So again, we're going to have a second way of describing this, which is more general. And once we get off the surface of the Earth, that we have another problem to worry about. So as you get further away from Earth, the gravitational field decreases. So we're starting to get into field forces, and they're kind of a funky thing in physics and fascinating thing to understand as you get into fields in gravitation, in electrical fields, and we get into magnetic fields in this class. So the idea, though, is that there is this sort of field that exists. So if we have Earth, and we think about Earth just by itself with no other mass there, that Earth sends out this gravitational field in all directions. And if you were to put a mass someplace, that mass would experience that attraction to Earth. And this is the curious thing about fields. The only way that we can detect that they're there is by sticking something there and seeing what happens to it. So in this case, we can tell that there's a gravitational field by putting mass there, and the same with it's going to be true for electricity. The only way we can tell this electrical field is put a charge someplace and see what happens to it. So we're going to represent fields in a couple of different ways. So one way is with these arrows. So notice that the arrows are indicating the direction of attraction. So another mass will be attracted to Earth. And those lines going into Earth are showing the direction of attraction. So the red rings here are going to be areas that will have the same magnitude of attraction. So no matter what mass I put on one of these red lines, if I put it anywhere on that red line, it will exhibit the same magnitude of attraction. So these concentric rings. And notice that as you get further away, those red lines get further apart. So it's given a hint that this is not a linear relationship. So roughly the way that we represent these fields, or any field, is that the denser the arrows are, so the black arrows pointing, the denser they are, the stronger the field. And the further apart they are, then the weaker the field. So you can see closer to Earth, I have a stronger gravitational field, and further away, I have a weaker gravitational field. And hopefully you kind of know this already, right? So if you get really far away from Earth, that you're not going to be as attracted to it as much as if you're very close. And we'll have an explanation for that. So the thing we want to get into is describing the gravitational field that doesn't depend upon the Earth being on the surface of the Earth. So let me go back to, where do you go? Here it is. So in this case, we're going to describe a gravitational field, and this is what we're going to do. So what's going to be important? Well, I can think about this a couple of ways, but I'm going to say my gravitational potential energy, right? So last time we talked about force of gravity, and we have Newton's universal law of gravitation, which says if you take some constant g and multiply it by the product of any two masses divided by the square of the distance, or you'll end up having this equation that shows the gravitational attraction between these. So I can determine the gravitational attraction, and notice that this is kind of similar on the surface of the Earth. This is the same as saying m1g, right? So our constant g here, there's 9.8, it's really representing this gravitational field, right? So I can write this as m1 times g. This is the mass of the Earth over the radius of the Earth. This is equal to m1 g. So this value g tells us two things, right? It's going to tell us the acceleration that an object will experience, and it's also going to tell me the strength of the gravitational field that's at Earth, at the surface of Earth. So my gravitational potential energy, I'm going to have a very similar thing, right? I can think of this as force times distance, but my gravitational potential energy for any two masses is going to be similar, where I'm going to have that same constant times the product of the two masses. I'm going to divide it by r naught squared. Right? So r naught squared. Right? So hopefully you recognize that this is sort of like work, right? So I take this force and multiply it by distance, or r in this case, right? I'll be left with this. So it's sort of like work, force times distance. But I'm missing one important thing here. And the challenge is that as I get further away, I end up having less gravitational potential energy. So mathematically, this gives me a problem. I need to solve this with a negative sign. So this is really important, that the negative sign means that when I have very large r, so when I'm infinitely far away, right, this is going to be 0. Right, so here I am, here's Earth, and I'm going to go to the edge, right, Earth. I'm going to go to the edge of the universe. So when I'm at infinity, infinitely far away, my gravitational potential energy is 0. So think about this, right? If I lift something off the surface of the Earth, right, it's gained potential energy. As I get further away, it's got more potential energy, right? So I could let it fall, and it would accelerate as it changes that potential energy into kinetic energy. So if infinitely far away is 0, as I get closer, it's got to be less than 0, right? Hence my negative. And as I get even closer, it's going to be even less than 0, so I'll have a larger negative number. So to make this work out, we have to be really careful that we have this negative sign here. So, but gravitational potential energy, very similar to the calculation for Newton's universal law of gravitation, but with the caveat that we put a negative sign in there to make it work out. So this will come up a couple of ways. One of the ways that it often comes up is thinking about escape velocity. So let me walk through this particular challenge of describing escape velocity and give you an example of how to use this. So here I am, I'm on the surface of the Earth, right? And I want to send a rocket off into outer space, and that's a rocket. And I want it to go far. I want it to escape from the gravitational pull of the Earth, right? So I'm going to give it some kinetic energy. And I want that kinetic energy to be all converted to potential energy at the edge of the universe. And that's 0, right? So this is what I'm going to do. I'm going to say the energy that I start with is going to be equal to energy that I end with. And at the end, I'm going to end with only gravitational potential energy, which is going to be 0 at the edge of the universe. I'm going to start with two things. I'm going to be careful here. So I'm going to start with kinetic energy, yes. But also notice I'm not at the center of Earth, so I'm going to have some distance. And again, my potential energy, just like my gravitational force of attraction, right? I can pretend that all of this mass is at the center of that mass, and mathematically it works out perfect. So so this case, I have some potential energy. If I was right at the center of the Earth, I would have no potential energy. But if I'm further away, I've gained some potential energy. So now I'm going to have some potential energy that I start with and some kinetic energy. And this is where the negative sign becomes really important, right? Because I can't have negative kinetic energy, but I do have a negative value for potential energy. Right? So I'm not saying that there is a thing as negative energy. I'm just saying that the way that we account for potential energy, that I can have a negative magnitude on that. Okay, so now I'm going to plug in some numbers, right? So I'm going to have negative g mass of my rocket times the mass of the Earth divided by the radius of the Earth, right? So that's my potential energy. I'm going to add to that whatever kinetic energy I need, 1/2 mass of the rocket times velocity. So this is my escape velocity squared. And for this to get to the edge of the universe with no potential energy, that I'm going to set that equal to 0. So you may notice one thing. So oftentimes in energy, we'll get a mass to cancel, and this is certainly true when we don't have springs. And I can plug in some numbers that come with some escape velocity. So in the end, I'll end up with velocity is going to be square root of, what's this going to be, 2 times the radius of the Earth divided by g times the mass. Yeah, I got that backwards. So the velocity is going to be root 2g mass of the Earth over radius of the Earth, not squared. So you'll get an equation for escape velocity, so you'll have to get going this fast if you want to escape from the gravitational pull of the Earth. Notice if I'm on a different planet, you can use the same equation. You just need to know the mass and the radius of the planet. You don't need to know gravity that acts on the planet. It's taken into account with the mass. Anyway, this is one way that we use conservation of energy and gravitational potential energy. A lot of times we'll look at difference in potential energy. And hope that's helpful. Talk to you soon. Bye.